Electromagnetic induction. When the magnetic flux linking a conductor changes, an EMF is induced in the conductor. This phenomenon is called electromagnetic induction. Here we have practical demonstration of electromagnetic induction. We have a coil and a magnet, and coil is connected with galvanometer. When a magnet is moved through this coil, then we can see a deflection of galvanometer, which shows that EMF is induced in this coil due to the movement of this magnet. Because due to the movement of magnetic flux through this coil changes, and due to change in magnetic flux linking in a conductor, EMF is induced. This phenomena is known as electromagnetic induction. The basic requirement for electromagnetic induction is the change in flux linking the coil or conductor. So when flux linking the coil or conductor changes, then EMF is induced in the coil, and this phenomena is known as electromagnetic induction. Activity. In order to demonstrate the phenomena of electromagnetic induction, consider a coil C of wire connected to a galvanometer. Near the coil is a stationary bar magnet. In this figure, you can see a coil C and a magnet, that is stationary magnet, near to the coil, and coil is connected with galvanometer. When the magnet is stationary, the galvanometer shows no current, no deflection. So there is no source of EMF in the circuit. When this magnet is stationary, which is placed near to this coil, and we can see there is no deflection through the galvanometer, means there is no current, there is no EMF generated in this coil. If we move the magnet towards the coil C, the galvanometer shows deflection in one direction. If we move the magnet away from the coil, the galvanometer again shows deflection but in opposite direction. Here, when a magnet is moved towards the coil C, so galvanometer shows deflection towards the positive side, and when this magnet is moved away from the coil, then galvanometer shows deflection in opposite side, in negative side. By the movement of magnet, flux linking the coil changes, and hence EMF is induced in the coil. Due to induced EMF, galvanometer shows deflection. Flux can also be changed by the movement of coil. We can move this coil for changing the flux, magnetic flux. The product of number of turns of the coil and the magnetic flux phi linking the coil is called flux linkage. So flux linkage is equals to N into phi. Phi is magnetic flux linking the coil and N is number of turns of coil. So we can move this magnet, or either we can move this coil to change the magnetic flux. In both the cases, flux will be changed and we will have EMF through this coil. Another demonstration of electromagnetic induction: when a magnet moves inside the coil and the coil is connected with the galvanometer. So galvanometer shows deflection due to the movement of magnet, and the magnet is moving inside the coil. North pole of magnet is going inside the coil, so the deflection of galvanometer is towards right. And when the north pole of magnet is moving away from the coil, north pole coming out of the coil, the deflection of galvanometer is towards left. When the south pole of magnet is going inside the coil, the deflection is towards left, and when the south pole of magnet is moving outward or outside of the coil, then the deflection of galvanometer is towards right. So due to the movement of magnet, deflection of galvanometer is shown in this demonstration, and due to different poles of magnet, polarity of galvanometer also changes. We can demonstrate electromagnetic induction in another way. Here we have two coils. Coil 1 is connected with AC source and current is flowing through this coil, and coil 2 is connected with galvanometer. Here coil 1 is connected with AC source, so current is flowing through this coil, and due to flow of current there must be a magnetic field through this coil, because we know that whenever current flows through a conductor, then there must be a magnetic field due to flow of charges. And due to this magnetic field, we can have magnetic field through this coil too, because this coil is near to the coil 1. Coil 2 is placed near to the coil 1. Due to the movement of coil 1, the magnetic flux through this coil 2 can be changed. So due to the continuous movement of this coil 1, the magnetic flux linked with this coil must be changing, and due to change in magnetic flux linked with coil 2, we can have electromagnetic induction, phenomena of electromagnetic induction, that is, we can have EMF through this conductor or through this coil. So EMF as well as current is induced through this coil, that can be shown by the help of this galvanometer when current through this coil is changing, and or due to the movement of the coil, flux linked with this coil 2 is changing. Due to change of flux linkage, we can have EMF as well as current through this coil. But when magnetic flux through this coil will be zero or will be constant, then there will be no EMF and there will be no current through this coil, because EMF is induced in this coil only when magnetic flux linkage with this coil is changing. When a magnet is moved through this coil connected with galvanometer, then the magnetic flux linkage through this coil is changing. Due to change in magnetic flux, the induced EMF is generated through this coil, and current is also induced in this coil, and that induced EMF is directly proportional to rate of change of magnetic flux, delta phi divided by delta t, that is rate of change of magnetic flux, and it is also directly proportional to n. N is number of turns of coil. Here proportional sign is equals to k, and k is constant, its value is 1, where k is constant and its value is 1, and we get EMF induced in this coil, is equals to N delta phi divided by delta T. That shows that EMF induced in the coil is directly proportional to rate of change of magnetic flux. It depends upon the change of magnetic flux per unit time and number of turns of coil. When we increase the number of turns of coil, then EMF induced through this coil will be increased and rate of change of magnetic flux is increased, so EMF will be also increased. The induced EMF is always opposes the change in flux. The direction of induced EMF is given by Lenz's law. Another important thing is that the induced EMF is in the direction that opposes the change in magnetic flux. This induced EMF always opposes the change in the magnetic flux through this coil. So this EMF induced in the coil opposes the cause which has induced it, and the cause is obviously magnetic flux, change in magnetic flux. So this EMF wants this magnetic flux to stop, and the direction of induced EMF is given by Lenz's law. So in equation given by Faraday, we use negative sign, and the negative sign in the equation represents Lenz's law, and we will discuss it later. Seismometer. Seismometer is used to measure the intensity or strength of earthquake. An earthquake is a shaking of Earth's surface known as the crust. The Earth's crust is made of huge rock plates which can shift to cause an earthquake. Most earthquakes happen when two rock plates meet, creating friction. The force is so strong it will send shock waves through the ground, creating an earthquake. So when the rock plates in the earth crust meet, then they create friction and the force is huge. Due to this huge strong force, we get shock waves through the ground, and these shock waves create earthquake. To measure the earthquakes, we use a device called seismometer. One kind of seismometer is called inertial because it is based on Newton's first law. The other kind of seismometer works on the principle of electromagnetic induction, and now we are going to discuss this kind of seismometer in which we use principle of electromagnetic induction. Seismometer transforms received vibration energy into an electrical voltage. The relative motion between a magnet and a coil induces an EMF in the coil that is proportional to the relative motion, velocity of the relative motion. So in seismometer we use a magnet and a coil, and due to relative motion of magnet and coil, EMF is induced in the coil, and this induced EMF in the coil is directly proportional to the velocity of relative motion. When we have greater velocity of relative motion, then the induced EMF is greater. Electromagnetic seismometer. Here we have a fixed magnet and a coil, a moving coil. This coil can be moved, and this movement of coil and the magnetic field of this magnet causes a EMF, and EMF is induced in this coil. The voltage or EMF in this coil is proportional with the velocity of the coil in the magnetic field. So when the velocity of the coil increases, we will have a greater EMF induced in the coil. The magnitude of EMF is also proportional to the strength of the magnet used and the number of turns in the coil, because we know that EMF is directly proportional to number of turns of coil, and it is also directly proportional to rate of change of magnetic field. An electromagnetic seismometer has a coil fixed to the case and move with the earth. The magnet suspended by spring has inertia and does not move instantaneously with the coil. So magnet is stationary and the coil is moving, and this movement of coil depends on the earth crust. So due to the vibration of earth crust, this coil moves and its velocity increases with the increase in vibration of the earth, and the EMF is induced in the coil. And we can have this pattern on the paper which shows the intensity of the earthquake.